Okay. Thank you all for coming tonight. So just to make sure you're in the right place, this is deep learning in Python using Chainer. Okay, everyone's at the right meetup? Okay, good. My name is Chris Min, and I'm an employee of Preferred Networks, which is the company that is hosting the event tonight. So I'd like to give you an idea of just how the evening is going to go, first of all. So this is intended to be a 2-hour workshop. It's intended to be hands-on, which is why hopefully you've bought a computer, and we'll also log on to the internet, and I'll be giving you ideas and tasks to do actually as we go through this. So there's not going to be any formal breaks. So if you need to go to the bathroom or something so you can focus here, or if you want to get some more pizza, I think there's a little bit left back there, please feel free to do it so that you can come back here afterwards and focus. So I'd like to get an idea before I start of what the level of experience is in the room. So how many people have already used Chainer before? Okay, mostly new. Okay, thanks. So how many people have not used Chainer, the framework Chainer, but have used a different framework, TensorFlow or PyTorch, or have coded from scratch or something like that? Okay, fair number of people. Okay, and how many people have done no deep learning, no neural network coding before and are going to be learning about it tonight? Okay, another group of people. Okay, good. You're in the right place. Welcome, all of you. So Chainer is the framework that we're going to be using today. It's the framework that was developed by my company, Preferred Networks. Although at this point it is open source, and while we continue to development for it, and all of our engineers and researchers use Chainer for their daily work, anyone can contribute to and use Chainer and install it. So one more thing is, as you have questions, ask. So trust me, we have a good number of people here today. So if you have a question, someone else probably has the same question. So on behalf of both of you, feel free to ask as we go through it. So that's, to make that real, does anyone have any questions right now about how the evening's going to go, or whether there's any more pizza or anything? Pretty good? Okay. So I'll jump into it then. So the first thing that I wanted to do is give a look at basically the structure of training. So this is just to show you how a deep learning model fits together, specifically for the Chainer model. So as you can see, there's a number of parts to it, and they fit together kind of like a Russian doll or so. There's certain things that go inside of other things that work together. And we're going to start from this model from the very most inside. We're going to start with the data sets and learn something about the data set. We'll get an example data set. And then we'll put that inside of an iterator, which then gives samples and batches from that. Then we'll make a model, which then is actually your neural network model that then is the thing that does the actual learning. But the model itself doesn't improve itself, so we'll put that inside of an optimizer, like stochastic gradient descent, or Atom, or something like that, that will be used to tune the model so it can learn. Both of these things go inside of an updater that is then called by the trainer that does the actual learning. So you don't have to memorize all this just yet, and actually there's no test later anyway. So I just wanted to give you the overall picture first. And then in addition to that, there are extensions that the trainer can use so that it can publish logs, give you a picture of what your graph looks like, or show you how your progress is going as the actual training is happening. Okay. So the first step, and I encourage you to press play on the first button right away, is to install CuPy and Chainer and NumPy. So this is installing the deep learning frameworks. Once you hit this button, as you can see over on the left, you'll have a lot of install spam that will go by. And it'll take maybe a minute or two to install. The good news is that this is being installed, all of it on the Google servers, so we don't need to worry about bandwidth here. It's being installed remotely, and you're just seeing a window onto it. So if you click the little arrow next to that first install chainer and CuPy and NumPy, then it will start installing. The first line is to install some libraries that are missing from the CUDA library on Google Colabs. The next line is to install CuPy, which is what allows for the calculation on the GPU. Then after that, it's installing chainer itself, and then importing it into Python along with NumPy, which is a mathematical tool that's used for doing calculations. Okay? And then at the end of it, you should see a print, C print runtime info. And this is the next one. You can go ahead and run this. It'll show you that we're on chainer 4.0. NumPy 1.4, and then CuPy, and then the CUDA build should be 8,000. Okay? So if I can have your attention up here again, we're going to look at the data set. So the data set that we're going to use, as you might have heard in deep learning, the data that you have is one of the most important things about your learning. And sometimes it's, well, actually, usually the amount of data will trump the actual framework that you use. So if you can get 10 times the data, you will do better than someone who maybe has a better algorithm but doesn't have as much data. So it's very important. So for our lesson today, we'll be using a data set called MNIST. Actually, we're going to be using fashion MNIST. So those of you who have done deep learning or learned about it before might be familiar with MNIST, which is just the numbers from 0 to 9. And it's kind of a classic data set that's used by a lot of people. And it's actually this year 20 years old. And you know what? It's not that useful anymore. It's too easy. So instead of MNIST reading numbers from 0 to 9, we'll be using fashion MNIST. Much more stylish. And it basically then goes over the, let's see here. It goes over pictures of fashion which have been given by Zoolander. So it has 10 different fashion items: t-shirts, trousers, pullovers, dresses, coats, sandals, other things. So the pictures are generally more difficult to recognize. And so as a result, it's more useful to test on to see whether your model is really learning or not. So this is the data set. So I'm going to go over this line by line and tell you what we're doing in this program so that you understand how we're working with this. And then I'll ask you to go into this and change some things so that you're familiar with the data set. So the first thing we do is download the data. So I recommend, again, you go ahead and push the play button on this, because this is the second thing and only thing tonight that will take time. It takes about 2 minutes or so to download the fashion MNIST data set. So once you push the button to play this, it'll start with these lines over here, downloading, and it will download it to the Google Colabs so that you can see it. So go ahead and push that button now while I continue to talk about this. So as part of this, as it's downloading this, we're going to be getting the training and the testing set. So fashion MNIST, like MNIST, has about 70,000 examples, of which we will be using 10,000 for testing, and 10,000 examples for validation, and 50,000 for the actual training. So this is something that often deep learning we forget that's very important, is that in order to do deep learning training, you need 3 data sets. You need to have your data set that you're actually doing the training with, and then you need to have 2 holdout data sets for doing testing on, and validation. So as we go through working on a deep learning, it's traditional, or you always will be going against a validation data set that you didn't train on to see whether your results are improving. So the goal of deep learning is never to learn the data set you have. It's to learn about data sets that you haven't seen yet. It's about examples that you don't know yet. And so if you just train and test on the same data set, then you're going to fool yourself into thinking you've learned it when all the model has done is memorize the existing data you have. So you have one data set that you use for validation to see whether you're actually improving against unknown new examples. But as you'll find as you work with deep learning, it's never a once and done thing. As you continue to work on it, you'll change the model, you'll change the hyperparameters, the learning rate, the number of nodes you have, the number of layers you have, the type of model you have. But as you're doing that, each time you'll put it up against the validation set to see whether the validation has improved. But what you're doing then is now you're again using the validation set, so it will become not unknown. You'll be learning the validation set in addition to the test set. So you should have one more set that you barely ever use, which is the test set. And so I think oftentimes when I see papers on deep learning and they talk about getting a certain percentage, I often wonder whether that's their validation set or whether that's their test set, and they just basically learn the test set by modifying the hyperparameters. So we're going to do better than that here. We're making 3 sets. So this first line gets you your training set and the test set, and then we take the training set and we take another 10,000 sets off it to make the validation set. The next 2 lines are going into basically loading up matplotlib so that we can display pictures like we have over here to the right. And then we just take the first example from the training set. I know that on yours it will be different from mine because I used an old picture because it had the downloading on it. You should see a picture of a t-shirt, I think, if I remember right. Okay, you're doing great. That's the right answer. Okay? And then I have a couple of lines here that were there just for me to find out what kind of data I'm looking at. So I encourage you at this point to get familiar with the structure of the data. So the first thing I did is I looked at the shape of the training data. So I got NP-shape train. And you can see the output over here, or you'll see it below on your thing, that we have, this says 60,000, but it should be 50,000, as I said. This isn't updated on the slide. So we have 50,000 lines with 2 items per line. And each of those lines then is X, the 2 items, is the example itself, and then Y, which is the correct label for it. And then I took a cut of X itself. X, as you can see over there to the left there, is 784 lines long. So it's a single array, 784 long. And to save you the math, that's 28 times 28. So basically these are 28 by 28 pictures in black and white. And you can see some of the values of them over there to the left. These are the 28 by 28 values. It's in black and white. When you go to the display below and display it with the matplotlib in a 28 by 28 square on a grayscale, then it looks like a shirt or a shoe. Questions about the data set? Okay, no, you want to get into examples. Okay, so change the number. Try some different numbers, get some different pictures so you can see what the items in the data set look like. So who knows how to change which picture you get in the example from the text above? Go ahead.
You have to change the index on the training variable?
Right. So if you change the index here for which one we picked, then that'll give you a different picture. Okay, so you can take a look at some of the different pictures and see what other things look like there. And as you do that, you'll also notice that the raw X will change as well, so then you'll have different values over here for the colors. So these numbers that I picked here are just a random slice in here from the middle of it, because if you pick the first row, it's kind of boring, they're all 0, it's all black. So instead I picked like line 200 to 220 out of 784. So something else you can play with is trying to pick a different slice of the data so you can see some different lines there. Okay. Okay, I put this on the bottom just in case anyone was too fast and wanted to do something difficult. So another thing to try would be to take the image and flip it right to left. You can't do this with anything I've told you so far. You'll need to search on the internet or use a NumPy function to do that. But if you feel like going further, that's something else you can try. Okay, so let's continue on. So the next thing we get to is the iterator. So these things will get actually a little faster. As you saw, loading the data took a little bit of effort. But the iterator is pretty straightforward. Okay? So from Chainer, we import the iterators. The iterator decides the batch size. So this is basically, the iterator will take your data set, and when asked by the trainer, will give it a certain number of examples to do the training on. And we need to make a few iterators so that we have one for the training and the validation. So underneath the iterators, we use the serial iterator. So there are 3 different kinds of primary iterators. There's a serial iterator, there's a multi-process iterator, and there's a multi-thread iterator. For our purposes, we only have one GPU. We're only going to use the serial iterator. The multi-thread or the multi-process would be if you have multiple GPUs or if you have multiple nodes with multiple GPUs. So for this point, we'll use the serial iterator. It uses the specific data sets then, and then the batch size. And it's fine to go through the data set basically in order, just as they come. Yes?
So could you back to the previous slide?
Sure. Oops, sorry, that's the other way. Here we go.
I missed why we are generating this picture.
Okay.
So
There's no purpose other than so that you know what your data set is.
this is the data set to draw on.
Just a picture from the data set.
Oh, I see. I get it.
Not-
So not learning anything.
No. You're learning something. Model is not made yet. Sure. Okay. Other questions? Okay. So now we're going to get into the model itself. I think a fair number of you have already looked at some kinds of frameworks, so you're probably familiar with how models look in general. The first thing I'd like to show you is this is the newest function that we just released in Chainer actually last week. So last week we just released Chainer version 4, and with that we released the sequential model, which makes it easier to create your models. So I wanted to show this. This is actually a picture from Chainer docs, which hopefully you'll be looking at later. But it shows you actually some of the ways that you can put together a model. And I'll give a more example of later, but basically you can define it as a sequential model with linear stages, functions like sigmoid or relu. You can add models together sequentially. You can repeat layers so that it's easy. And also you can append layers to other layers to build your model. So I think it's easier to understand that with an example. So then this is the next example from within the model. And so actually the model definition, first we have a few lines just to give ourselves parts of the Chainer language. So Chainer models are built from functions and links. So functions are basically just mathematical functions. This can be like a sigmoid function, which is basically just like an S shape then that has an activation function. Or it can be a relu function, which is then going to be 0 up until 0, and then will be linear afterwards. Just mathematical functions you use as activation functions. So this decides whether the neurons fire or not. Then the other thing that it can handle is the different types of layers. So a linear layer, which is simply a fully connected layer. I'm not going to have enough time to draw the connections on this. You might have seen maps like this before of all the layers connecting to each other. So this is a fully connected layer. It's going to be a linear layer. And so in this definition, we're making a very simple one for the fashion MNIST. But basically, we define a layer as a sequential layer, and then it has 100 nodes in a linear layer. So basically, this layer is going to have 100 nodes. And the activation function then will be a relu, which is basically the linear function to 0 and then goes up for the activation function. Okay? So if you haven't studied neural networks before, this might be fairly new. In fact, This will be very new. If you have studied before, you'll be familiar with this. For right now, we're not going to go much more into it other than to know that these are functions that are available. Chainer has a number of functions like this that you can use. But the other important thing that we imported from Chainer was links. So links are basically the hidden parameters. Each link can have a function to it, but it also has hidden parameters that will be learned over time as the model gets smarter and smarter. So as you can see, when we make our first layer, it's a sequential layer, and it has a linear function, a linear link. This is with our hidden parameters. And then it has a ReLU function for the activation function. Okay? And then we repeat this layer twice. So we have two 100 node linear layers. And then we go out to a linear layer with just 10 nodes on it. And this would be our output then, which will tell what kind of apparel you have. So to put that into a map that's simplified, we have one layer with 100 nodes on it, another layer with 100 nodes on it, and then we have a layer at the end with 10 nodes on it. And all of these layers are fully linked. And this is basically the model that we're going to train. Okay? Who has questions about that?
Any reason why we were choosing 100, 110?
No. This is part of the devil's in the detail, is that there is no right answer for this, or at least you have to have a lot of experience. So in general, I think that we have 784 incoming units, and then those are fully connected to 100 layers. But this is one of those things that there are trade-offs. In general, it's better to have more deeper layers, as deep learning. But I also wanted this to calculate while you're still here. So we didn't do more than that. So this 2 layers, I think, will give time for a reasonable runtime during the session. But later on, I'll be inviting you to change those and see if it gets a better result.
Okay.
Okay. So continuing down, so this is the function that defines our model for us. And then below that, we actually call an instance of the model. So we make an instance of it and call it model. It's a clever name. And then part of the sequential is it gives you the ability to do a printout of the model. So you can make sure that it looks like you think it should look. And so we flatten the model, which flattens out the repeating layer so it has a better description to it, and print it. And then this gives us the output that we have down below that, which shows that we have a linear layer with 100 nodes to it, followed by a ReLU, another linear layer, a ReLU, and then a 10-node linear layer. So the next thing we need to do is we need to calculate the loss for this. So the model as it is right now will give you a basic prediction of what it is that you're trying to identify. But in order to do the training, we need to figure out how far off our prediction was from the correct answer. And this is called the loss. So we have the model losses. This is a classifier type model. So it's going to give us a vector from a value from 0, an integer, sorry, from 0 to 9. And we want to know when we find out the right answer, how wrong it was. If we were very confident and it was wrong, we need to correct that so we'll have a high loss. If we got the right answer, then that's great. We don't need to correct as much. But maybe the model wasn't very sure, so we want to tell it, yes, that's the right answer. So you make a model loss based off the classifier. Then the next part is working with the GPUs. So Chainer can work both on GPUs and CPUs. If you're wondering which to use, the answer is if you have a GPU, use it. The GPUs are going to be about 10 times faster than a CPU for pretty much anything you're going to be doing in deep learning. That said, my computer is a Macintosh, and if I'm local, Macintosh GPUs there's no software for them, so you really can't use the GPU effectively, so I do it on the CPU. Which is one of the reasons why I like using Google Colabs, because they provide a GPU. The ID is set as 0, so if you have more than one GPU on your device, maybe boards or something, you could have GPU ID of 0, 1, 2, 3, 4. If you're using the CPU, you set that to -1. So since Google Labs provides us with a GPU, we'll set it to 0. And then we want to move our model of the loss to the GPU so that we can do the training on it. Okay? Okay?
Excuse me.
Yes?
We define, like, each node has a rel function.
Yes.
And then we will learn something, and then what we will include, like, we will change the function, the threshold.
The rel function is, as a function, it has no variables that change. It's just a rel function, that's all it does. The one that will change is the L linear, which has the variables, the weights in them. So the L linear has variables in it, and you don't see it here because this is a high-level framework, which means you don't need to worry about it. That's where the variables that are held for the various weights, and also the biases, if you're, depending on how familiar you are with machine learning. So it's the links then that contain the parameters that are learned.
So something I don't know, they become.
Yes. And something else that we won't get too deep into because we're not teaching you how to code Chainer, we're teaching you how to use it. We'll then take care of the actual learning over the back of that. Okay? Yes?
Actually, two questions. The first one, we don't have to define the input shape of data.
Yes.
So it's automatically.
Correct. So you're correct. There's something that I've left off here because it's because I like things simple. But there's actually one more layer here, which is the input layer, which, as we talked about before, is 784, right? 782. Okay. So basically, there's the example that comes in, which is 782 examples, and that is fully linked to R100. But Chainer, if you don't input 2 values for the node, it basically assumes the incoming layer is fully linked. So just like we haven't put on the last layer, the layer before it was 100 nodes, the last layer was 10. We don't need to tell it that the first layer before it is 100. It knows that because it saw the layer coming in. You can put it, by the way, but I don't like writing numbers twice. And the second question?
The second one, we do not define any function for the last layer, an activation function.
No. So,
Just take the output of it.
so the last layer, as a result, it will be an activation. It'll be put through the ReLU, and it will have a wide range of numbers. And basically, we'll see it later, but we'll take the maximum value as the best guess. Okay?
So which means that we are defining the hidden 2 layers and
Yes.
the 1 out of 2 layer.
Correct.
Right, thank you.
Sure.
Question.
Yes.
The reason why the number of last layers is 10 is because the number of layers or the levels are 10.
Correct. Yeah. So we have 10 different items of clothing. So this will output, basically, we'll have 10 different values at the last layer. And then we'll take the maximum value of that as their best guess for that's probably the category it falls into. Okay. Yes?
If I would like to normalize the input data, Chainer provides some utilities.
Yes. Yes, so in this case, we're using a very curated data set of MNIST, right? So you saw the values are from 0 to 1. That's a reasonable range. But of course, if you're using, say, RGB or something which had 0 to 255, you would want to normalize that down to like a -1 to 1 range. Correct. Yes?
The type of the input data is NumPy arrays.
Yes.
Which is compatible.
Yes. So CuPy is the back end of Chainer. CuPy is a drop-in replacement for NumPy that uses NumPy syntax to do calculation on the GPU. So it makes it very smooth. If you're familiar with NumPy, this will all look very familiar. Okay. Okay. So I wanted to show this as another way of doing the same model. This actually is from the Chainer documentation. We haven't updated this yet to use the sequential model, so it's written in the old style for writing a model. This is the exact same model. Basically, we have here, we're defining a layer to do fashion mnist, and we have the units coming in defined as 100. We have the units going out as 10. We define the layers first in initializing it, saying we have a linear layer. The none here means use the previous layer as the framework for that. And then the mid units then is 100. We have 2 layers with 100 units, and then the out is 10 units. And then when it's called, this is when it actually does the calculation and uses ReLU between these lines and then returns the last line. So this does the same thing. It's written in an older format that I don't like as much as I like the sequential. I find that to be more intuitive. You might have to use this kind of a format if you're doing a more complex neural network that has branching or forking or merging. If it has skip layers or other things, sequential doesn't support that. So in that kind of a case, you would need to write out the network more like this. Also, this will give you more ability to put in statements and error commands or look at the model as you're going through it, so it can be easier for debugging if you have something that's more complex. I prefer the sequential though, but if it's higher level. Okay, so the next thing we need to do is we need to attach an optimizer to our model. Actually, before I do that, any other questions about the model or anything else? Yes?
In PyTorch, there's like an explicit need to move the model to the GPU.
Yes.
Is that implicitly changed?
No, actually that's this last line right here. Model loss to GPU.
So it's like, it takes a bundle of like the collections and...
Yes. So Chainer is so named because basically all of these things are linking together as we build them. So you notice that when we did the model loss, we basically took our entire model and put it inside of a classifier. So then when we move the model loss to the GPU, that pulls basically the entire model with it, so it can all be done in the GPU. Okay. Yes?
Is there any way to control what goes into the GPU?
If you control what you want to, like, yes, you can. Later on as we go through this, for example, the inference and other things, you'll see that there are separate steps for doing that, and there are also commands for moving things to the CPU as well. So if you want to bring something back from the CPU, that's also possible. Okay. Right, so back to the optimizer. So in this case, for those of you who know about machine learning, you might know there's a number of different optimizers. So this is how the network actually learns, is that each time it goes through and gets a new, tries to make a guess at something, okay, I think those are a pair of trousers, gets the answer and then sees how far off it was. You need to go, it goes through a mathematical process then to correct all of the weights to try and make a better guess next time. And this is the job of the optimizer. The most common optimizer that's used in textbooks is stochastic gradient descent, or SGD. It's basically doing a derivative at the point and then following it backwards. I haven't put it here because it's one of the earliest, but it's not considered to be the best today. So I've used Atom as the optimizer. So if you were to put SGD here in all caps, it would be using stochastic gradient descent instead. Other optimizers you might have heard of would be Momentum, RMS Prop. There's a number of them. Many people have strong feelings about which is the correct one. Atom is one of the more current ones that's frequently used. There's a number of variables or hyperparameters that are set with this. There's a learning rate. There's a decay for the weights and other things. But I think it's fine basically to use the defaults for those. If you go to the Chainer docs, you can see what all the parameters are and you can change those as you want. I think the default usually works fine. So now we're going to link both the iterator and the optimizer together into the updater. So we're getting it ready to put it into the trainer. And the updater then is again just one line, where we pick an updater, or we're using the standard updater. As before, when we work with the iterator, there are two other kinds. There's like a multi-process and a multi-thread type updater. Because we're only using one GPU, we use the standard updater. And into the updater, we're going to pass our training iterator, the optimizer, and again, we're going to tell that we want this done on the GPU. So it'll pass it to the GPU to be done. Okay. So now we almost have everything we need. The last thing we're going to look at is the extensions. And there are a number of different extensions that can do different things. The ones that I thought were most useful that I use all the time are listed here. So this is actually defining our trainer with the extensions. So I import the extensions as E, because I got tired of writing extensions. And then we define a trainer by calling chainer, training, trainer. And first of all, we put in our updater so that it knows how to update. Next, we tell it to run for 50 epochs. So one epoch is basically one run-through of every example that we have. So it's going through every example, seeing whether it's right or wrong, and then updating the model accordingly to improve the weights. So there's no magic behind 50 epochs. Sometimes that's the right answer. Usually you need more, but we'll get some good results out of that. Out result, this is basically telling it to use a directory called result to store the results in. And then we have our list of extensions. So the first extension that we need to have is the evaluator to tell how we're doing, and this uses our validation set. Again, we're leaving the test set off to the side. We're going to use the validation set so that we don't end up inadvertently learning our test set. So we use the validation iteration to do the evaluator. Our model loss to say how we did, and again, this will be done in the GPU. We want to dump a graph of the overall process. So as I said, as you code this in, when it actually runs through it, it will learn what your neural network graph looks like and will give you a picture of it, which we can use for verification that it looks like we want it to look. You have the right number of layers. Those layers are doing the right thing. You'll see the dimensions of each of those. Then log report is basically just each epoch then is doing a log of what the results are. And this is required for some of the other things like the plot reports and the print report. So the plot report will give us a plot of our loss, so we can see how the loss is going over time, both on our training set and also our validation set. And then we'll have another plot report that will show us our accuracy, which will show again how we're doing on the training set and also the validation set. And then the last thing we have is we want to have a print report so that each epoch we can see what the status is just as it goes. This is so that it shows you something as you're going along, how much time have you spent, whether you need to know whether you need to wait a couple of minutes, a couple of hours, a couple of days before your training is actually done. This is the output to the screen so you can see it working. So when you push the run button, this is what you should see. But not as fast as this. So it'll start training. You can see that this is about 26 epochs, took about 2 minutes, a little less than 2 minutes. So in about 4 minutes you should see all 50 epochs run. And just to clarify what you're seeing here, we have our loss on the training set, which is the main set, and our loss on the validation set. And then we have our accuracy on the training set, which is the main, and then the accuracy on the validation set. So you see as this goes down, this is the most important column is right here, because this is your accuracy on the validation set. So the main set, the training set, will get more and more accurate. What you really want to know is how well is it learning to see examples, classify examples that it hasn't seen before. And that's what you see over on the validation accuracy. And as you can see, we started at about 83.7, and it generally gets better as we go down here to about 88.5. As I said, the fashion MNIST is a more challenging data set. For comparison, they had, I think, 1,000 people try and do this data set. They had 3 people categorize each one of the pictures, and they picked whichever 2 people agreed on. And the human accuracy was 83.5%. So the neural net is already smarter than people. So it is quite a challenging. I think they probably had a lot of difficulty between like high ankle boots and sneakers is I think one of the ones that I get confused with. Okay, so while that's running, let's go ahead and jump ahead. So this is what I told you about. It was going to dump a graph. So this is showing you then what the actual graph looks like so that you can see how the graph is put together. And it gives you the matrix size for each of the elements and then goes through it. So some of these might not be as familiar if you haven't worked with neural networks before. The B is the bias. And then the next one over is actually the data itself. You can tell because we have 700, we have a batch of 128 examples because we set the batch size up the iterator at 128. And then the next part is the 784. This is the number of lines we have in each example. And then the last one is actually the weights. So this is the variables that it's learning and tuning as it goes through each iteration. These are combined together into a linear function, which then gives us a new value of 128 for a number of examples, times 100 units, which is the number of nodes we have within the linear layer. That's put through a ReLU to the next layer. And now this is the incoming data. And this is, again, has 100 weights for 100 nodes and 100 bias factors. Goes through a linear function, which then gives us a new array. Again, goes through ReLU. Now we're heading into the second hidden layer, which basically is the same as the last hidden layer. Then that goes out to the 10 floats. So this is our last layer with, again, the number of batches. And we have a softmax cross entropy, which then tells us what our actual answer is. And this softmax cross entropy is actually what changes the numbers into saying this is the answer. So it's telling, well, actually this is giving us the loss. This is telling us how far wrong we were or how close we are. Any questions about the graph? Yes?
Is there a reason why in the last layer the softmax isn't explicitly implemented?
The softmax actually is implicitly implemented, not explicitly implemented within the classifier. So you're right. You notice there was never actually a point where we said softmax. It's part of this categorization of the loss. So that's part of the classifier. So there's a couple of other things it's doing there to turn it into a loss calculator. So the softmax is included within that layer. And it's not within our network itself over here because we're going to want to use the same network for inference later. So calculating the loss is different from actually making a guess of what it is. So there's another calculation. When the model itself returns back, okay, this is what I think you have, then the softmax calculates how wrong or how right it was. But when we're just trying to find out what we have, then all we want to know is that one. So we've added that as a separate layer that's only done when it's doing the training.
So if we would have the binary classification where we would need a sigma,
yes.
It wouldn't change anything up there, but in the classifier.
Correct. Then you'd use a binary classifier down here. Yes?
Can you define your own classifier?
Yes. Of course. It's all Python, so it's all available, and you can define your own classifier. You can define also, there's a number of other functions if you want to use a different loss function. This is using soft cross entropy. If you want to use a different function, there's a number that are built in, or you can code your own. Yes?
Is one epoch?
Epoch, yes.
Oh, so the one epoch means include something and output something, the one epoch.
So one epoch means that our training data set is 50,000 examples. One epoch means that it has tried every single one of those examples once.
Oh, yeah.
Yeah. So it's done 50,000 calculations in batches of 128, because that's how its size of each iteration is. But an epoch means it's done a full run through the entire data set, except for the holdouts.
Is there another unit? That's one that we specified the epoch somewhere.
Mm-hmm.
So
let's see. Right. There are other units. If I remember right, you could also write seconds there. I'm not sure whether minutes or hours, but I know that at least seconds. So if you wanted to say, okay, run for an hour, you could write 36,000 seconds. Right. So you can limit it by a certain number of things. This is basically telling the trainer when it's going to stop. Okay. Okay, I think we're good for the graph. Okay. So here's our here's the actual loss that we see. So one of these is for the actual training set. There we go. One of them is for the training set, which is this one. You can see that over time it's getting better and better at the training set. But if you look at our validation set, you can see that it started getting better at the validation set, and then it started actually getting worse at the validation set. Basically what this is telling you is that your model is starting to memorize your data set, and it's starting to overfit. So there was a point in here where it had the best results, which was about here, but then it starts actually, it's memorizing the particular examples as opposed to learning a general rule. And we'll talk a little later about ways to address that. And you can see that also when we look at the accuracy. So if you look at the scale over here to the left, you can see that while on the main data set, the training data set, we've gotten up to almost 97% accuracy, which seems great. Hey, we're doing fantastic. But on the validation set, it peaks out at about 88% or so. And it doesn't seem to be able to learn any more than this. Part of this is because we only have 2 layers within our neural network, and we're not doing some of the fancier things. And depending on time, we'll get to some other ways that we can improve this. Does anyone have any questions or comments about this part? This is one of the key charts. It's going to tell you how your model is doing. So tuning this so that you can improve your validation accuracy is one of the prime jobs of tuning your neural network is. Yes?
Does loss have a negative correlation with the accuracy, or is it kind of same concept?
They're similar. So the question is loss different from accuracy or the same thing? So interestingly, you'll notice that while our loss is getting steadily worse here, in other words, when it gets an answer wrong, it's getting it very wrong. If we look at the accuracy, actually, it's about the same. So the accuracy in some ways is determined, okay, you have a number of 1, and it has a probability for each possibility. But it picks the highest probability and says this is the answer, and that calculates the accuracy. But the loss is going to look, okay, yes, you got the right answer, but you weren't very sure about it, and you gave these other ones almost the same amount, would be a high loss. Whereas if it said this is the right answer, it's the only answer, and then everything else I give a 0 probability, then that would be a 0 loss. So loss can show you more of what's behind it. If you look at the accuracy, you might not understand, but if you look at the loss, you can see that you're clearly overfitting. It's getting better and better at your training set, but it's getting worse at the validation set. And so there are a number of ways to deal with this. You could add more layers, maybe change the batch size, your learning rate, some other things. Okay.
So in this case, if we want to use this model just as a classifier, should we care loss? I mean,
yes.
Based on the accuracy, we get the same high accuracy. So why care about loss in that case? I mean,
I would say that 80% accuracy is not enough.
So I mean, you can look at the loss so that you can have some more idea to improve it.
Yes. Yeah, 88% for this is, while it's better than human, as I said, humans get 83.5%. Still, the goal is going to, we'll work with some things later that can improve this accuracy.
And even use loss to have some idea.
Yep. Mm-hmm. It can show you more of what's going behind. You can see here that you're overfitting the model. Okay. And we can use dropout and some other deep learning things, or add layers to it is another thing that we can do to increase the depth of the model, or increasing the width so that we could add more than 100 nodes to the network is another thing we can try. So we'll get to that in a minute.
Okay, so
yep.
At the very beginning, we split the data set into the 2 sets, like training set and the validation set.
Yes.
So that results in these curves.
Yes.
But if the set is different, maybe for this line, for this curve, we chose this and this. But if the training set might be this one, and the validation set, we take this one. So the curve might be different. So, but. So,
all right. Let me see if I understand your question. Are you saying like more data is better? So we have 3 data sets. We have the training data set, which is 50,000 examples. We have the validation set, which is 10,000 examples. And then we have the, I need to make this training, okay. And then we have the testing set, which is then another 10,000 examples. So is your question if we were to train on the validation set? No. Like if we were to use different samples?
No, there's the combination of the separating the training set and the validation set.
Yes.
So the combination is different from this set. The curve might be different, so we are now focusing on the kind of overfitting.
Right.
But because it's overfitting that training data set.
Yes.
And maybe we chose the how can I say? There's some part of the training set and including all of the validation set for the training and some part of the training set to the validation set. The curve might be different.
There's no overlap between them.
Yeah.
Okay. So they're totally discrete sets. Are you asking if we had more examples here, whether the curve would be different?
No. I'm concerning is now we are focusing on the overfitting, but that overfitting is that training data set.
Yes.
So, which means that if we chose the different set of the training data set and the validation data set, the curve might be different. So, but the meaning of the overfitting.
Okay.
So just this kind of overfitting is caused by the choosing the dataset of training. But the training dataset is we at the beginning we chose that kind of randomly.
Right.
So that can be any set of the. So
I think he's talking about cross-validation. Why we need to do cross-validation?
Okay.
Please explain cross-validation. This is not cross-validation.
Right. So you're asking, are you asking why we had these held out, or you're okay?
Yeah.
Well, first of all, if we were to have a different random set, the answer would be the same.
Okay.
I know because we had a different set earlier today. When we first did this, I didn't have a validation set, and one of my colleagues told me you have to have a validation set. That's bad coding, so I added the validation set. So it's important to have, but I guess I think the real answer to your question is that this is robust to changes. So when I say that you need more data, this amount of data, or even both of this amount of data, is not going to help you. You always want more data, but you're going to want it in orders of magnitude. The question is not how could we get twice as much data, it's how could we get 10 times as much data. And that will improve your accuracy. But it's not worth it to compromise on your validation set or your test set to get different data. And you can do a different random. In fact, I recommend you try this when we get to the exercises in a minute. One of the things that we had when we chose our data sets, here we go, is there's actually a seed that's used to do the random selection.
Okay.
If you change the seed to something other than 0, you'll get a different cut.
Oh, yeah.
Go ahead and try it. So you can change that to another number, and then the picture over here will probably be different again. It won't be a t-shirt, it might be something else. It's just random. But I think that you'll find that your curves will look pretty much the same. We're talking about 50,000 examples.
Okay.
So it's unlikely to be moved by a different random set. If you had 100, I think it would make more of a difference. Does that answer your question?
Yeah, thank you.
Okay. Okay. Yes?
Blue line is using test data,
Training data, yes.
And then like validating using training data.
Validating using the validation data.
But using validation data.
Yes.
I wonder, so machine learning, use training data to train.
To learn, yep.
To learn. Then why they can include validation data because they didn't use validation data as training data.
That's intentional. We're trying to teach the neural network to learn a model that's generalizable. So you don't want it to just memorize 60,000 examples, which a computer can do. You want it to learn how to identify what something looks like, in this case, what the shirts or the objects look like. So in order to make sure that the model generalizes, we need to test it on examples it's never seen before. And that's what your validation set is doing for you.
And then for the right one,
the test set?
Test set is the main one, right?
You know, we haven't touched it yet. We're still holding it off to the side. We'll use it later.
Okay, I get it.
Yeah, okay. Good, okay.
One thing I want to add
yes, go ahead.
to his question. Chile had get a cross-validation data set random function. So you can create an n-fold data set which includes a different set of training and validation set, n-fold such combination easily.
Okay, if you use the threefold, like so separating three part of the three subset of the data set and folding, taking one is for validation data set and the rest.
All example are resampled from the same set. So for example, different combination of 50,000 training and 10,000 validation.
And
different set of
choosing a different
same number of the examples.
Okay, maybe I understand.
So data itself are overlapped, but validation set and the training set
overlap.
Same data are shared between those different sets, but the combination of training and validation is different.
So that is cross-validation.
Cross-validation.
And calculate the validation errors and take the average of the errors to see more confident validation results of them. Is a kind of cross-validation.
So there's another approach to doing the testing sets and the validation sets. Another approach is where you put it all into a huge bucket, and then you do stripes of it each time. So every time you go through the epoch, you say, okay, for this epoch, we're going to say this will be my training set, this will be my validation set, and all this will be training. And then the next time it goes through, you can do another striping. It's a different way of assigning which goes into which one. You always need to keep some out, but the ones that are kept out for validation are different through each epoch. But this is cross-validation, but it doesn't give you that much advantage over just having separate training sets. It's a little more complicated, so we've just done static training sets for this example. Okay? Okay. So, time for the hands-on part again. So now you've seen a model. You've seen how it works. You've seen the configurations that have been done with it. So now see if you can improve it. So if you remember, we had a validation of about 88% in our accuracy on the validation set. So I invite you to go into the model and try changing some things. Maybe change the number of epochs so that it runs for a longer time. Change the batch size to make it bigger or smaller. It's 128 now. You could change the number of nodes in the layers. If you think 100 is not the right answer, that there's a better number of nodes you should have in the layers, you can change that. Or change the number of layers. So you could make it so it's a deeper model. Then the last two are more advanced changes. So you could change the activation functions to something other than ReLU. So you could use a sigmoid function or a leaky ReLU or something else. Or then the last one is adding a regularizing function such as dropout or batch normalization. So as I've said before, there are actually no tests today. So this is all open internet. So as you're going through these things, especially if you're trying to do the last ones, use a different function, feel free to use the Chainer docs to see what other functions might be available or how you might do that. Feel free to use whatever you'd like to take on some of these trials and see how the model reacts. So you do need to be, each time you run it, of course, it'll take a time, so pick your what you'd like to change. And I'll give you some time to go ahead and try things like that. If you have a question as you're going through this or anything, please feel free to raise your hand, and I'll talk to people.